The last section of chapter 16 is 16.10. Now, there's no homework for it. 1610 just does, I think, a very responsible thing. It says, okay, we've learned a whole bunch of stuff, and sometimes it can kind of feel a little bit overwhelming, and it's just this like, how do I calculate this, and when do I do this thing, and when do I do that thing? And 1610 says, let's just take a step back and look at the big picture. And while we're doing that, let's just cover all 3 semesters of calculus. Why not? So, we start with the fundamental theorem of calculus. Way back when in first semester calculus, you learned this. Now, I phrased this in a specific way. I've said if you're integrating a derivative, very often it's stated as if you're just integrating f, then you get an antiderivative. I've chosen to really emphasize the relationship between this function and this function. F prime is obviously a derivative of f. That would make f an antiderivative of f prime. So this says if you're integrating a derivative over an interval from a to b, what you're going to get is an antiderivative evaluated at the endpoints and then subtracting. Okay. Now that was kind of mind-blowing at the time, and perhaps still should be. I want to just present that in a slightly different way. We were integrating over this one-dimensional region from point A to point B, an interval along the x-axis. Most of the time we're integrating left to right. It is possible, of course, that we're integrating backwards. That's totally fine. Okay. Notice this is one-dimensional. Okay. Its boundary, if I think of it as having a boundary, would be these 2 endpoints. So the boundary is just the set of points A and B, and points are actually 0-dimensional objects. Okay. So we don't usually spend a lot of time talking about the dimension of a point is 0, okay? But it kind of makes sense. It doesn't have any length. It's down one level from a one-dimensional line segment or a one-dimensional curve. Okay. And so what this does is this gives me a relationship between an integral over a one-dimensional region and working with a related function, not the integrand, but a related function on the boundary of that, where the dimension of the boundary is simply 1 less than the dimension of the region. And you'll notice the function that I work with on the region, which is one-dimensional, has a relationship to the function that I work with on the boundary of the region. It's a derivative. Okay. Now that sort of establishes a common theme. This semester we had 4 more theorems that built on this theme. So we had the fundamental theorem of line integrals. That said, if we were doing a line integral along C of a conservative vector field, so we had the gradient of some function, some potential function f, and we were doing the work integral for that. And let's just say that C was this curve that took us from point A to point B. Well, what we would get is simply that potential function f evaluated at B minus the potential function f evaluated at A. Now, once again, that's a relationship between 2 related functions. Here, the potential function f and its gradient, del f, okay, and 2 regions. The one-dimensional curve C and its boundary, which would be the endpoints, 0 and B. Sorry, not 0 and B, A and B. Now that, of course, is 0-dimensional. The dimension of the boundary is 1 less than the dimension of the region itself. So, of course, when I'm working on the boundary, I'm going to be integrating 1 less time. If I'm on a 1-dimensional region, I'm going to be doing a single integral. If I'm on a 0-dimensional region, it makes sense that I'm integrating 0 times. So once again, there's a connection between a region and its boundary and these 2 related functions. Now here, it's a little bit more complicated, but the function that I'm working with here, our potential function f, has as its derivative the gradient, del f. Now, I'm not just integrating the gradient, I'm integrating the gradient dotted with t, because my integrand needs to be a real valued function, and the derivative is a vector valued function. But there's a connection between the function that I work with on the boundary and the function that I work with on the region that has that boundary, and that connection has something to do with derivatives. It's not quite as direct as that's the derivative, it's the derivative dotted with t, okay, but it's got a connection through some form of differentiation. Pretty cool. Okay, I'm just going to go in the order in which we covered things, which is different from the order in which things were in the book. The next big theorem that we had was the divergence theorem. That was for flux integrals. That said, if I was working with the double integral over s of f dotted with n ds, I could instead do the triple integral over e of the divergence of f dv. So this was where we had a three-dimensional region E. You know what? I think I'm actually going to, even though this is the way I usually write it, I'm actually going to write it the other way. Triple integral over E of the divergence of f dv is the double integral over s of f dotted with n ds. That way I'm being consistent. Here I'm putting the regions, here I'm putting the boundaries. Okay. Now if I have a three-dimensional region, its boundary is a two-dimensional surface. Okay. So working over the region, I'd be doing a triple integral. Working over the boundary, I'd be doing a double integral. Now let's take a look at the connection between the functions that we're working with. Okay. Here I've got a vector field f. Now that by itself isn't my integrand. Things get more complicated once we throw in vector functions, because I want to be integrating a real valued function here. So I'm integrating f dotted with n. Okay. But if I look at f and its connection with the divergence of f, that has something to do with derivatives, because this is just a sum of certain partial derivatives of the component functions of f. So again, the function that I'm working with on the region as a whole is connected to the function that I'm working with on the boundary by some form of differentiation. Okay. All right, I like it. Then we did Stokes' theorem. Now that was for work integrals. We said if we were doing the integral around C of f dotted with t ds, we could work instead on the double integral over s of the curl of f dotted with n ds. Okay. So again, s would be some surface that's two-dimensional. So when I'm working with that, I'm doing a double integral. Its boundary would be a curve C, that's one-dimensional, so when I'm working with that, I'm doing a single integral. And if I look here, the vector field that's contributing to the integrand here is f. Curl of f, I'm calculating using a lot of the partial derivatives, because that's the del operator, whose components are the partial derivative operators, crossed with my vector field f. So the relationship between these functions has something to do with derivatives. Okay. And then we finally had Green's theorem. Again, that was working with line integrals, with work integrals. But that was just when we're working in two space. And then we were integrating partial of q with respect to x minus partial of p with respect to y. dA. Very, very similar. Here, this is no longer curl dotted with n, but you'll notice this vector field, p and q, would simply be its component functions. So f would be p, q in this case. Okay. And I'm looking at some partial derivatives here. Okay. So all of this is basically saying there's a big picture here. There's a connection between a region and its boundary. And the dimension of the boundary is always going to be one less than the dimension of the region that it encloses. Okay? And it turns out that I can work over a region with one function, or I can work over the boundary with a different but related function. And the connection between those isn't always quite as simple as whatever I'm working with on the boundary, I'm working with the derivative on the enclosed region, but it always has something to do with derivatives. Now it turns out, and this is beyond the scope of the class, but it turns out that what we learned as Stokes' theorem is actually little Stokes' theorem. There's a big Stokes' theorem. Big Stokes' theorem includes all 5 of these things. Big Stokes' theorem summarizes, hey look, there's a relationship between doing an integral of this function over a region and doing an integral of that function over the boundary. And it's able to say something a little more precise than the connection between the function has something to do with derivatives. Something called an exterior derivative. Defining that is way beyond the scope of the class. I didn't learn about that until grad school, and honestly, I don't even remember what the formal definition of it is. Okay? But essentially, Big Stokes' theorem says you can work with a function on the boundary of a region, or you can work with the exterior derivative of that function on the enclosed region. And what we've seen is just glimpses of that big picture in some specific cases. And I think it's kind of mind-blowing to see that these 5 really big theorems all have that common theme. So it's kind of neat to just take a step back. Really nice that the last section of the semester doesn't have any homework associated with it, but that we can just sort of take a look and bask in the glory of math. It's very cool that all of this stuff, which has caused some heartache along the way because it does involve some complicated calculations, all of this is really just encapsulating this one big picture, that there's this beautiful connection between regions and their boundaries and the functions that we can work with. It has been a pleasure teaching you this semester, most of the time. It's been somewhat difficult having to do it remotely. I much preferred getting to actually interact with you guys in person. I miss you guys. I'm sorry that we had to go through this, but I really am grateful to you for what good sports you've been as we made the transition to this online learning environment. I'm really grateful to you for making it as easy on me as you did. I know it was hard for all of us, but thank you very much. Good luck on your final exam. Good luck with your future studies. It has been a pleasure being your teacher.